Hey everybody, Trey here. Welcome back to another video. Today is April 3rd, 2024, the 50th anniversary of one of the most widespread and intense tornado outbreaks in recorded history, and that of course is the Super Outbreak of April 3rd and 4th, 1974. 148 tornadoes occurred across 13 states in a 24-hour period, surpassed only by the April 2011 Super Outbreak. However, the 1974 outbreak reigned supreme as far as tornado intensity goes. Nearly two-thirds of those 148 tornadoes were significant. 96 were rated F2 or higher, and 30 were violent. 23 F4s and 7 F5s compared to just 15 EF4 plus tornadoes in total in the 2011 Super Outbreak. 48 of the tornadoes in the 1974 outbreak yielded fatalities, with 335 deaths and over 6,000 injuries in all. Some of the more notable tornadoes from this outbreak include the Xenia, Ohio F5, which killed 32 people and destroyed most of the town, the Cincinnati and Sailor Park, Ohio F5, which lifted and swept houses clean from their foundations, and perhaps most notably, carried a pickup truck a half block over 5 houses before smashing it into the ground, and the nighttime Guin, Alabama F5, which was the longest duration F5 of the outbreak, and is widely considered one of the most violent tornadoes on record, killing 28. In this video, we're going to take a deep dive into the meteorology behind this historic event to try to piece together why this outbreak was so prolific and intense. As always with these case studies on older events, we unfortunately don't have tools such as high-resolution radar and satellite data to help us with our analysis, and we're forced to use upper air reanalysis data, which is an estimate of what conditions were like on April 3rd and 4th, 1974. Still, we should be able to get a good picture of what the environment was like during this outbreak, and because it's such a notable event, multiple journal articles have been written on it. I'll put a link to all the articles I mentioned in this video as well as some others in the description box below so you can do some research on your own. So without further ado, let's go ahead and get started. First, let's discuss how the stage was set for the April 3rd outbreak. We're going to go back to April 1st, 1974, a couple days before the event, to see how the atmosphere evolved in the days leading up to the 3rd. We'll start out at 12Z, 7 a.m. Central Daylight Time on April 1st at 500 millibars on the SPC's Violent Tornado webpage. The brown lines are geopotential height contours, and the blue lines are isotachs, or lines of equal wind speed. We started off the period with a bit of a shortwave and associated jet streak moving through the flow. This would induce a precursor tornado outbreak across many of the same areas that would be impacted by the April 3rd and 4th event. By April 2nd, the trough quickly moved out, replaced by a zonal flow regime in its wake, with the exception of continued troughing over the western U.S., where our next major wave was developing, and some modest ridging over the southeast. This pattern had been quite persistent over the preceding weeks, as evidenced by this map of the composite 500 millibar geopotential height anomaly for the month of March 1974. The blues and purples indicate below normal heights, while the greens indicate above normal heights, and you can see that there were generally below average heights across the western U.S., with slightly above average heights across the southeastern states, which suggests persistent low amplitude troughing in the west and persistent weak ridging across the southeast. As we know, what happens aloft influences what happens at the surface. This is a map of composite mean surface pressure for the month of March 1974. Once again, the blues and purples represent lower pressures, while the yellows, oranges, and reds represent higher pressures. Accompanying our persistent west coast troughing aloft was fairly persistent surface cyclogenesis east of the Rockies, and surface ridging and high pressure off the southeast coast. This somewhat anomalous pattern had some implications on the environment leading up to the super outbreak. First, strong, moisture-sweeping cold fronts were unable to intrude well into the Gulf of Mexico. As a result, rich, deep moisture was readily available to be advected northward into the U.S. well ahead of the event. In addition, the combination of continued surface low development out west and stubborn ridging out east yielded persistent southerly flow across the southern U.S. and Gulf of Mexico, allowing for a prolonged period during which that rich, low-level moisture could be advected northward. As the April 3rd event approached, a robust warm sector was able to easily advance inland, overspreading a broad region from the Midwest to the Gulf Coast. Even as the cold front associated with the April 1st system moved into the eastern U.S., the low-level flow quickly returned to southerly as renewed surface cyclogenesis occurred over the western U.S. Another impact of this persistent pattern was that we had fairly persistent westerly to southwesterly mid-level flow leading up to April 3rd, which ushered in a mostly undiluted elevated mixed layer atop the broad warm sector. As we often discuss on this channel, the EML is that layer of warm, dry, well-mixed air that emanates from the higher terrain out west and gets transported atop the low-level moist layer out east amid the westerly or southwesterly mid-level flow. This helps thwart thunderstorm development for much of the day until the cap erodes and allows instability to build effectively. Using this plot of 700 millibar flow and heights atop 700 to 500 millibar lapse rates, denoted by the shaded regions, you can see the continued advection of steep mid-level lapse rates emanating from the higher terrain of the central and southern plains into the region from the Midwest to the southeast, including this plume of 8 to 9 degrees Celsius per kilometer lapse rates that first appeared the evening before the outbreak. Notice how it rides that southwesterly mid-level flow and situates itself across the outbreak region by midday, yielding a broad area of burgeoning instability leading up to peak heating. Now that we've illustrated how the atmosphere was able to prime itself for widespread severe weather well ahead of time, let's dive into the meteorology on the day of the outbreak. After the April 1st event, that secondary trough in the western U.S. continued to amplify and march east, closing off and taking on a bit of a negative tilt by the morning of April 3rd. We've switched our data source to the Tornado Archive, which uses a different reanalysis method than the Violent Tornado webpage, but it matches up well with the 12Z 500 millibar map analyzed in Hoxett and Chappell 1975, a synoptic analysis of the 1974 Super Outbreak. We had a little streak of some slightly enhanced flow at the nose of the more expansive belt of stronger flow associated with the long wave trough, so you could consider this a bit of a lead shortwave. This shortwave continued to eject to the northeast, overspreading the Midwest by midday, providing the forcing for ascent for severe storm initiation in this region. The overall trough took on a bit of a positively tilted nature as the day progressed, but areas farther south, more removed from the lead shortwave, were still well within the exit region of the larger trough. Perhaps a more glancing blow from the trough across southern portions of the outbreak area yielded a more discrete storm mode, which, as we know, is more favorable for strong, long-track tornadoes. The storm mode also remained favorable farther north. The trough's positively tilted nature and overall motion toward the northeast tended to minimize height falls over the warm sector. As we've discussed before, height falls are when the geopotential height decreases at a certain location with time. Height falls lead to rising motion, which, as we know, is favorable for severe storms. Now, if you focus on any particular point across the outbreak region, notice how, as I replay the animation, the height contours don't seem to traverse east all that much over the outbreak region. In other words, strong height falls did not overspread the warm sector, allowing for forcing to remain on the somewhat weaker side despite the strong trough. This weaker forcing likely contributed to a more pervasive, discrete mode across the entire warm sector, more favorable for long-track tornadic supercells. We'll discuss more on storm mode in just a bit. At 300 millibars, we see beautifully defluent flow over a broad region from the Midwest to the southeast. We talk about defluence ad nauseum on the channel here. It's the spreading apart of those wind vectors in the upper levels of the atmosphere which creates a void. And to fill that void, air is brought upward from below, and that's how you get large-scale rising motion that can prime the atmosphere for storm initiation in a given environment. This defluent flow regime begins to overspread the region by midday, with generally south-southwesterly flow over Wisconsin, Iowa, and Illinois, transitioning to flow with a much more westerly component across Indiana, Ohio, and areas southward. Thus, we had an expansive region that was under the influence of this favorable synoptic scale rising motion. With strong westerly and southwesterly flow aloft traversing the Rockies several days prior to this event, we'd expect to see renewed surface cyclogenesis over the western U.S., and that's exactly what we got. The surface low rapidly deepened as we went into the 3rd, and given that the main shortwave and most notable defluents aloft were transitioning into the Midwest, the surface low took this path as well and remained intense. By 18Z, the low was centered near the Kansas City area with a warm front draped to the northeast through northern Illinois and southern Michigan. The actual synoptic cold front was somewhere back in here, while a well-developed dry line was draped southward through Missouri and Arkansas. Corfidi et al. 2010 argued that this boundary actually had the characteristics of both a dry line and a cold front, the result of a merger between a cold front associated with the lead shortwave aloft and a bona fide dry line. The cold front was most evident at 700 millibars. Notice the dip in the isotherms, or lines of equal temperature, which are the dashed red contours, across Kansas, Oklahoma, and Texas. At the surface, a dry line was evident from Missouri into Texas on the evening of April 2nd, and the two boundaries conglomerated into one during the overnight hours of the 2nd into the 3rd. For our purposes, we'll continue to call this composite boundary the dry line. Ahead of the surface low, strong southerly flow developed and continued to usher rich moisture into the region. Low to mid-60s dew points quickly advected into the Midwest, with some low 70s dew points across southern portions of the warm sector, which was quite broad given the optimal availability of the undiluted Gulf air mass. This, combined with the widespread defluent flow aloft, yielded a ton of real estate for severe storms to work with. Oftentimes, the overlap of favorable kinematics and thermodynamics tends to take place over a confined area, but in the case of this outbreak, we had an incredibly large region over which that favorable overlap existed. At 850 millibars, an expansive low-level jet overspread the region ahead of the deepening low-level cyclone. The pressure gradient between the low-level cyclone and the ridging off the southeast coast helped to maintain strong low-level flow throughout the day. A large plume of 40 to 60 knots of flow helped drastically increase low-level shear and maintain strong moisture advection into the afternoon. A nocturnal ramp-up in the low-level jet occurred, with a large pocket of 70-plus knots of flow developing near and after sunset, which helped to further increase low-level shear for the after-dark portion of the outbreak. Here's a progression of photographs overlaid atop surface-based Cape, denoted by the shading, throughout the day on April 3rd. We start off with ample instability already well north up to the Ohio River, and very enlarged photographs were common, which is not all that surprising given strong low-level warm advection and the intense low-level jet already in place. Instability continued to rapidly advect northward into the afternoon, and large looping photographs remained common across the region. As the low-level jet ramped up at and after sunset, photographs enlarged further, especially across the southeast. Let's take a look now at some observed soundings from across the region to see how the environment progressed throughout the day. We'll start off at Dayton, Ohio. Here's the morning sounding from 12Z, 7 a.m. Central Daylight Time. Not much to see here yet. We were well north of the warm front at this time, 56 over 32 at the surface, so this was not a representative sounding from the actual warm sector. But watch how much the environment changed by evening. Here's the evening sounding from 0Z, 7 p.m. Central Daylight Time, and we see a much different profile. Thermodynamics were still a bit on the meager side, but certainly adequate for severe weather, 72 over 60 at the surface thanks to efficient warming and moistening as the day progressed. But look at that wind profile. We go from this at 12Z to this at 0Z, a drastic enlargement of the low-level photographs as the low-level jet moved in and strengthened over the region. Our 1-kilometer wind had jumped to about 65 knots by this point. Now, while there's ample veering and strengthening of the winds in the lowest few kilometers of the atmosphere, over 700 meters squared per second squared at 0 to 3 kilometers storm relative helicity, there's not a ton of directional shear in the lowest kilometer. In other words, the photograph is fairly straight below 1 kilometer with very strong speed shear, the changing of the wind speed with height, but little turning. Generally, you might expect this to be somewhat unfavorable for tornadoes, but this type of speed shear dominant low-level photograph tends to be fairly common with tornado outbreaks in the Ohio Valley region. Let's move south to Nashville. Here's the 12Z sounding, and we see a classic loaded gun profile. Deep, moist layer extending well above 850 millibars beneath a bit of a capping inversion. This is evidence of that large EML plume we talked about earlier. Very dry, well-mixed air with steep lapse rates and a fairly deep layer above 700 millibars or so. That led to ample instability, about 2,000 joules per kilogram mixed layer CAPE, already in place on the morning of April 3rd. The wind profile, though, left a lot to be desired. Only about 20 knots of 0 to 6 kilometer shear, well below the margins for supercells, and limited low-level shear, but the stronger flow aloft was still off to the west. This would change by 18Z, 1 p.m. Central Daylight Time, when photographs lengthened and enlarged as the mid and upper trough impinged upon the area. 0 to 6 kilometer shear was now in excess of 60 knots with significant curvature in the low levels of the photograph, about 300 meters squared per second squared effective storm relative helicity. Instability was on the increase as well. We continued to warm and moisten at the surface, with temperatures rising into the low 80s and dew points into the mid 60s. As the forcing from the trough arrived, that prior capping inversion was lifted and cooled, and by this point we were fully destabilized with nearly 3,000 joules per kilogram mixed layer CAPE. Couple this with the impressive wind profile, and you had a fairly textbook environment for significant tornadic supercells, which were, once again, able to occur over a very broad region given the vast expanse of the warm sector. Much of the same at 0Z, although low-level winds did start to veer slightly as the low ejected off to the northeast. Still, a very favorable environment for strong, long-track tornadoes was maintained well into the evening. Here we are at Jackson, Mississippi, which was a bit west of any notable tornadic activity, but I want you to focus on how the thermodynamics changed throughout the day. At 12Z, we have that classic loaded gun sounding, but much shallower moisture than at Nashville. By 18Z, that moist layer had deepened slightly while the cap continued to slowly lift and cool, and by 0Z we had drastically deepened that moist layer, extremely deep moisture up to about 700 millibars. This was streaming northward into southern portions of the risk area, helping to maintain the significant tornado threat into the evening across parts of the mid-south and southeast. This is a classic evolution of the deepening of the moist layer throughout the day, as subtle synoptic ascent lifts and cools the capping inversion, priming the environment for storm initiation. Finally, at Montgomery, Alabama, we see a similarly favorable environment persist, with strong instability thanks to that elevated mixed layer and continual warm moist advection, and an improving wind profile with time. As described in Corfiti et al. 2010 and Locatelli et al. 2002, the 1974 super outbreak was comprised of 4 main bands of convection, the first 3 of which produced the entirety of the tornadoes during the event. As shown in Figure 5 of Corfiti et al. 2010, the first convective band originated on the evening of April 2nd as scattered high-base thunderstorms that formed along the dry line in southern Oklahoma and North Texas. As they encountered richer moisture that night, storm coverage increased and an east-northeast moving squall line developed, producing isolated severe hail and wind near the Red River along its tail end as it traversed into Arkansas and southern Missouri. By dawn, the band had strengthened into a forward-propagating convective system, although many of the storms in the line were elevated within the intense background warm advection regime. The northern portion of the line began to accelerate, reaching a forward speed of 60 knots by early afternoon, followed by the acceleration of the southern portion of the line thanks to new storm development ahead of it in western Tennessee. The band produced the first tornado of the outbreak around 14:30 9:30 a.m. Central Daylight Time, a brief but strong spin-up northwest of Indianapolis. The band fractured into 2 distinct areas of convection between 15 and 18Z on April 3rd, a northern portion and a southern portion separated by a gap that occurred over eastern Kentucky. The southern segment produced the second tornado of the event, an F3 east of Chattanooga, Tennessee, just after 19Z. Hoxett and Chappell 1975 attribute the fracture to an area of large-scale subsidence or sinking motion over eastern Kentucky, but Corfiti et al. 2010 suggests that the strengthening and backing of the flow at 850 millibars locally enhanced the warming and drying downslope flow off the Appalachians across this area during the afternoon. The persistence of this first convective band has been traced to a gravity wave or similar feature called an undular bore. Miller and Sanders 1980 discovered a persistent small-scale pressure perturbation that traveled with the band from western Arkansas to the western Appalachians, illustrated by the small dips in pressure traces denoted by arrows at 3 different stations just after 14Z: Fort Wayne, Indiana, Louisville, Kentucky, and Birmingham, Alabama. In addition, visible satellite imagery reveals a well-defined arc of mid-level clouds coincident with this perturbation that appears to foster additional convective development as it moves east. Gravity waves can occur when air is forced to rise within a stable atmosphere. Locatelli et al. 2002 hypothesized that, in this case, the gravity wave or bore may have initiated as the cold front associated with the lead shortwave encountered a classic loaded gun thermodynamic profile over the southern plains. With the aforementioned strong EML in place through much of the morning, the atmosphere may have remained hostile to storm development had the gravity wave not acted as the forcing mechanism needed to lift parcels above the cap. In the wake of the first convective band, a second convective band developed around 15Z in northeast Arkansas and southeast Missouri, thanks to a combination of ample surface heating in the wake of convective band 1, notice the cloud breaks behind the gravity wave, continued intense warm moist advection, and subtle ascent ahead of the incoming shortwave. This second band initiated well ahead of the dry line in the open warm sector. Locatelli et al. 2002 attribute the formation of this second convective band to a cold front aloft, which they identified via a subtle wind shift and strong temperature gradient, as evidenced by the tightly packed isotherms over Missouri and Arkansas at 700 millibars, although Corfiti et al. 2010 dispute these findings. Assuming there was some sort of cold front aloft, we can see how discrete or semi-discrete storms would be the favored mode along it. Convergence was subtle along this boundary, and when we draw in our front along with the ambient deep layer shear vectors, notice the decent degree of perpendicularity between the two, especially along northern portions of the front. These two factors likely fostered a more discrete storm mode, allowing for a higher likelihood of strong, long-track tornadoes in a rapidly improving environment. Given the strong instability and blossoming deep layer shear, storms within this second band quickly became supercells with cloud tops exceeding 50,000 feet. The first F5 of the event was spawned by this band and struck DePauw, Indiana around 1920Z, and over the next 2 hours the band produced 2 more F5s that struck Brandenburg, Kentucky, and Xenia, Ohio. This second band produced the majority of both overall tornadoes and violent tornadoes in the outbreak. Storm coverage increased toward the north within the band thanks to slightly stronger synoptic forcing and weaker capping with northward extent. After 23Z, most of the intense tornadic activity began to focus south of the Ohio River, where slightly higher dew points and a bit broader of a warm sector resided. Also, diffuse thunderstorm outflow boundaries appeared to be the initiation mechanisms for much of the convection in this portion of the outbreak. These boundaries featured weak temperature gradients across them due to very rich low-level moisture and were oriented quite parallel to the mean flow, allowing them to remain stationary and provide corridors of enhanced low-level shear along which supercells could track for long distances. In addition, because deep layer shear vectors were fairly parallel to the outflow boundaries, discrete supercells, a product of the more subtle synoptic forcing and the diffuseness of the boundaries themselves, were able to train along these boundaries and produce multiple significant tornadoes. This setup made it much less likely for supercells to be undercut by their own outflow. This was illustrated in this region as an F5 tracked across several northern Alabama counties over a 51-mile path just after 0Z, and a subsequent F4 took nearly the exact same path just a half hour later. In addition, the devastating Guin, Alabama F5 remained in progress for 102 miles and was spawned by a long-track supercell that initiated in east-central Mississippi. Tornadic activity within Band 2 continued into Tennessee after midnight, and the outbreak finally began to wind down just after sunrise on April 4th, when the final significant tornado of the event, an F2, occurred in western North Carolina. Shortly after the second band developed, a third convective band took shape around 16Z along the dry line from west-central Illinois to the St. Louis, Missouri area. As stronger ascent ahead of the lead shortwave overspread the dry line, storm initiation was quickly realized once convective temperatures were breached, given the fairly weak capping in place. Given moderate instability and intense wind shear, these storms rapidly became supercellular, initially producing baseball-sized hail, including in St. Louis, where the costliest hailstorm to date occurred. Tornadic activity commenced within Band 3 just after 18Z with a brief F0 near Morris, Illinois, southwest of Chicago, followed by two F3s by 20Z that tracked into east-central Illinois. Just after 22Z, Band 3 produced an F4 that became the longest-tracked tornado of the outbreak, with a path of 109 miles, devastating the town of Monticello, Indiana. This appears to have been influenced by a subsynoptic scale low, or mesolow, that developed at the intersection of this third band with the synoptic warm front. Notice the slightly more backed surface flow across northern Indiana around this time. This mesolow tracked off to the northeast with continued significant tornadic activity ahead of it from southern Michigan into Ontario. Once again, a relatively discrete storm mode was maintained given the weak background height falls and favorable shear vector orientation with respect to the initiating boundary, which was the dry line. A fourth convective band developed ahead of the dry line immediately ahead of the surface low from northeast Missouri into eastern Iowa around 17Z. Given much more meager moisture in this region, the fourth band was fueled mostly by cold air aloft near the center of the upper trough. Storms within this band were low-topped and failed to produce tornadoes. While we don't have high-resolution radar data to analyze from this event, we do have models that are able to resolve what the radar might have looked like back then had we had today's technology in place. This is a simulation of radar reflectivity from 6Z April 3rd to 6Z April 4th, 1974, created by one of my viewers, Brian Bernard, using the Weather Research and Forecasting, or WRF, model. Big thanks to him for creating this and sending me this data. I'll put a link to his website in the description box below so you can check out this data on your own. Again, this is a model simulation, so it's not a perfect representation of how the event progressed, but it at least gives us a decent idea of what things might have looked like 50 years ago today. We'll start off just after midnight on April 3rd. We don't see much of the forward-propagating convective system that comprised Band 1, except for perhaps some remnants that moved across Missouri, Illinois, and Indiana on the morning of April 3rd. We then see the beginnings of convective Band 2 across southeast Missouri and southern Illinois by 16Z. Convection becomes widespread along this band over the next several hours, while Band 3 simultaneously develops over Illinois after 17Z. Notice that in both of these bands, while convection is organized in a linear fashion, we maintain numerous semi-discrete updrafts within the band rather than a solid squall line. This again was due to the aforementioned weak height falls over the warm sector and favorable shear vector orientation with respect to the initiating boundaries. We do also see some semblance of activity within convective band 4 across Iowa and Illinois. This convection, as we mentioned, was much lower topped and thus appears less robust on the model. Activity picks up along southern portions of convective band 2 going into the evening hours and continues across eastern Tennessee after midnight. Here's a progression of the updraft helicity swaths associated with the modeled convection. This tells us which storms acquired rotation, with the reds, pinks, and blues indicating stronger updraft rotation. Updraft helicity is not a direct indicator of tornadic activity, but with our knowledge of how favorable the background environment was on this day, we can assume that strongly rotating supercells, in other words convection with intense updraft helicity tracks in the warm sector, would likely have produced tornadoes, many of which would be significant. As the animation progresses, we can see evidence of each convective band, with some weaker signals in convective band 1 that produced the first tornadoes of the outbreak, and then much stronger updraft helicity streaks from convective bands 2 and 3 as they traversed across Illinois, Indiana, and Ohio. Southern portions of band 2 light up as well, with very lengthy updraft helicity swaths along that favored corridor from northern Alabama into Tennessee. Here are some of the actual radar images from the WSR-57 located at Cincinnati, Ohio during the 1974 outbreak. This wide view shows multiple discrete supercells ongoing at once. Even with such primitive technology, you can see several textbook hook echoes associated with these storms. Zooming in, we see two intense supercells, one near and northwest of the radar site, and one at the edge of the domain to the radar's northeast. This was the Xenia supercell as the F5 was in progress. So that's going to wrap things up for this video. There's so much more we could have covered, including how the 1974 event compares to other historic tornado outbreaks. We'll save this for a future video, but hopefully this video showed you why this outbreak was so prolific. There wasn't one glaring ingredient that made this such an efficient tornado-producing setup. Instead, it was one of those rare events where every single forecasting box is checked. Potent mid and upper level trough with ample defluence aloft, stout elevated mix layer, a rapidly deepening surface low with a large reservoir of rich Gulf moisture to advect northward over a broad area, intense low-level jet, and several subtle forcing mechanisms to promote discrete and semi-discrete supercells. In the vast majority of even the most potent-looking severe weather setups, one or two ingredients might be missing, but not with the 1974 super outbreak. Every ingredient was present in spades, leading to one of the most prolific tornado outbreaks in recorded history. It's been 50 years since the 1974 super outbreak, yet it remains the gold standard for tornado outbreaks in the United States. With that, thanks for watching, and we'll see you in the next video.